All right, well, welcome to another calculus lecture. In today's lecture, we're going to continue our discussion of limits, and in particular, we're going to talk about the various properties that limits have, and then we're also going to do a few calculations with limits just to sort of get our feet wet and get the idea of how these computations sort of go about. Okay, so properties of limits. So throughout this, f of x and g of x are just going to be functions, and I'll denote by c just some real number. So and maybe some other letters in there too for just real numbers. So for a real number, I don't know, a, the limit as x approaches c of a times f of x, so here I'm just going to take my function and scale it by some quantity, this is equal to a times the limit as x approaches c of f of x. And I should also note that we're not going to prove any of these. You can just take all of these as gospel and just go with them from there. So what this is saying is that the limit, I can take a constant and just pull it outside as something multiplying the whole limit expression. So maybe just for clarity, I'll put parentheses around this. So you can see that if I take the limit as x approaches c of just something scaled by a constant, that constant can essentially come out front as just multiplying the entire limit. So the next property, so this is just something having to do with constants. The next property is to do with sums and differences of limits. So we have that the limit as x approaches c of f of x plus or minus g of x, we can do a sum or a difference here. So the limit of a sum or difference is equal to the sum or difference of limits. So this is going to be the limit as x approaches c of f of x, and maybe just for clarity we'll put parentheses around this, plus or minus the limit as x approaches c of g of x. And again, this plus is the same as this plus, this minus. If I take a plus here, I put a plus here, same thing with the minus. Okay, these two properties together actually say that the limit operator is a linear operator. So constants can be moved in and out, and you can break them apart as sums or differences. Third property, this has to do with products. So the limit of a product is, well, perhaps if you're thinking of how this plays out, maybe you think that the limit of a product should be the product of the limits, and you would be correct. The limit breaks apart into products like this. So the limit of a product is equal to the product of the limits. Same thing with quotients, though there is one sort of nuance that we need to discuss. So the limit as x approaches c of f of x divided by g of x, this is equal to, and there's no way to concisely write this with multiple lines, so I'll do this as neatly as I can. X approaches c of f of x divided by the limit as x approaches c of g of x, provided that, well, what's the thing that we need to clarify here? We need this expression in the denominator of this fraction to be non-zero. So provided that the limit as x approaches c of g of x is not equal to 0. Okay, so you can break apart a limit of a quotient as the quotient of the limits, provided that the limit of the denominator is not 0, because otherwise you're dividing by 0, which we don't allow. Fifth, and this has to do with composition of functions. So if f of x is continuous, So here we need a continuous function. Then the limit as x approaches c of f of g of x, so here I would be taking the output of g of x and using it as the input for f. This is equal to, well, what can I do? I can take the function outside and just evaluate the inner limit. And then plug whatever this limit is into f to get my my limit, or to get the full expression for the limit. Okay, so this will turn out to be useful in a couple of our computations. But these are the main sort of properties for limits that we are going to use. Okay, and you could sit down and sort of derive all these from the definition of the limit that we gave in the last lecture, but for our purposes, we're just going to use these. We're not going to prove them in any way. Okay, so next thing I want to do is to do a few examples of calculations with limits, because there's a few of these in your homework, and one of the main things that you should take away from calculus is how to do computations with limits. So example computations, or calculations, however you want to say that. All right, and I'll do two of these. So evaluate the following limits. And what I want to do is I want to show all my steps, because you have to do this in your homework. So show all steps. So just for this first little bit in the course, when we do limit calculations, I want us to make sure that we're showing every single one of our steps in somewhat brutal detail. So that's what I'm going to do here. So let's do the limit as x approaches 1 of 2x squared plus cosine of pi times x. Okay, so if I want to compute this limit, well, there are a number of things we could do, and the order in which we do them is a little bit arbitrary, but we'll do them as follows. So first of all, I can break this apart as a limit or a sum of limits. So this is the limit as x approaches 1 of 2x squared plus the limit as x approaches 1 of cosine of pi x. And then now I have a composition here, and I have a scalar here, so we can rewrite this as 2 times the limit as x approaches 1 of x squared. So all I've done is I've taken this 2 and pulled it out front of the limit. And then in the second one, cosine is a continuous function. Sine and cosine are both continuous. So I can pull this cosine out front of the limit and evaluate it like that. So plus cosine of the limit as x approaches 1 of pi x. And then note also, x squared is a continuous function, or at least the raising something to the power of 2 is continuous. Or I can think of this as the limit as x times x, and so I can break it apart as a product of limits. So, and then I have a pi right here, which I can take out front of the limit. So this is 2 times the limit as x approaches 1 of x squared. And then we'll pull the pi out front of here in this limit, so plus cosine of the limit, or I'm sorry, of pi times the limit as x approaches 1 of x. And this is the level of simplification that I wanted us to get to. So now we just have a limit as x approaches 1 of x. And so when you have this, what you can do is just plug in the 1 here. So because x is a continuous function, I can simply just evaluate this by plugging in the 1 in clearly the limit as x approaches 1 of x should be 1. So this is 2 times 1 squared plus cosine of pi times 1. Well, 2 times 1 squared is just 2. And then cosine of pi, well, pi times 1 is just pi, so cosine of pi is negative 1. Okay? And there we go. We're done. We have calculated this limit, showing in somewhat gruesome detail all of our steps. Later on in the course, I won't demand that you show this much work when computing limits, but for now, this is the amount of detail that I want you to show in your calculations. Okay, let's do another one of these. This time, we'll do a little bit more work here. We're going to have to do a little bit more work. So we'll do the limit as x approaches 2 of x squared minus 3x plus 2 over x squared minus x minus 2. Now, in the previous one, I just sort of jumped right into the limit, and in general, what you can do sort of to begin is you can just try to directly substitute this. So that's what we'll try here real quick, just to see what should our answer be at the end, and then we'll fill in the details after we know sort of what we're working towards. So over here, we'll do some scratch work. So if I just try to plug in 2, I want to see what I'll get here. So I'll get 2 squared minus 3 times 2 plus 2 over 2 squared minus 2 minus 2. And what is that? Well, 4 minus 6 is negative 2, plus 2 is 0. 2 squared minus 2 is, that's also 0. So if I were to just start going at this and using my limit laws and breaking apart everything, I would end up with a 0 over 0 at the end, which is not sensible. So maybe what we want to try and do is actually try, and we have 2 polynomials here, so let's actually try and factor these first. So if I think about how to factor x squared minus 3x plus 2, I think about 2 numbers which multiply to give me positive 2, and whose sum is negative 3. And that is, well, negative 1 and negative 2 satisfy that. Their product is positive 2, and their sum is negative 3. So this is x minus 2 and x minus 1. And then we can do the same thing for the bottom. I think about 2 numbers whose product is negative 2 and whose sum is negative 1. Well, that's negative 2 and positive 1. X plus 1. Now, what I'd like to do is actually just cancel out these x minus 2's. And I can do that so long as x is itself not equal to 2. If x is equal to 2, I have a 0 over 0, and I'm not allowed to do that. But what's one of the main things that we know about limits is in the limiting operation, you're never at the point 2. X is never equal to 2 in the limit. You are only around the point 2. You never actually assume the value 2 in the limit. You just get arbitrarily close to it. And so we can actually write this as the limit as x approaches 2 of cancel these out. X minus 1 over x plus 1. And now we continue our analysis. So this is now a quotient, and notice that if I were to evaluate the limit at x as x goes to 2 of this thing, I'd get 3, and that's not 0. So I can do the, I got a bug on my table here. We can break this apart as the quotient, and I'm not doing this in the neatest way possible, but hopefully it still comes through. So we have a quotient of limits, and now I have a sum of things here. So this is a limit as x approaches 2 of x minus the limit as x approaches 2 of 1 divided by the limit as x approaches 2 of x minus the limit as x plus the limit as x approaches 2 of 1. Well, we know how to evaluate these first two, but what are these guys? Well, the function 1 doesn't change with respect to x, and so the limit as x approaches anything of the function 1 or or just any sort of constant function, this could be 100, 1,000, or whatever, I'm just going to get this number back out. Same thing for, we know how to evaluate these guys, so we can execute the limits at this point. So this is going to be 2 minus 1 over 2 plus 1, which is equal to 1/3. Okay? And so that's how we can do a limit calculation where maybe we can't quite just, set off and start applying all of our limit operations because we would get 0 over 0 in the end. Well, usually if that's the case, there's some sort of algebraic trick like factoring or combining fractions that would allow us to actually be able to compute this limit and get a number out of it. Okay, so the next thing that I want to talk about, and there were a couple of topics I wanted to get to in this video, but I'm not quite going to have time, or the video would just be very long if I did. The next thing that I want to talk about is one-sided limits. And this will be the last topic that I cover in this video. We'll do another one later on for the other topic. So one-sided limits. So one-sided limits, well, we sort of already hinted at what these things might represent with one-sided continuity. And one-sided limits are just, well, I look at the limit, but I'm only coming in from one side. So let's see, maybe we'll put this as a definition. So the limit from the, we'll start off with left of f of x denoted by, actually the limit from the left of f of x as x approaches c. I actually have to put this piece of information in here. Denoted by. And the way that we'll write this is the limit as x approaches c, and then we'll put a little minus sign here to indicate that we're coming from the left, which on the number line is coming from negative infinity. That's where the negative here comes from. So this is the value of the limit as x just comes along from the left. So how do we want to say this? Is a value of a limit as x assumes values only to the left of c. And likewise, the limit from the right which we define as, or we denote by the same thing, except instead of a minus, we're going to use a plus. So the limit as x approaches c from the right, so with a plus sign of f of x. This is defined similarly. I'm not going to write out the whole thing again, but x is now going to assume values only to the right of c. So this is defined similarly. Okay, now that's a very sort of informal and abstract definition, but let's maybe draw some pictures to get an idea of what we mean by this. So example, compute the left and right hand. This is another way of saying this. The left and right hand limits, or limit from the left and from the right, means the same thing. Left and right hand limits, assuming f of x has the following graph. And the picture for f of x we'll do is something like this, where maybe I'm at -1, -2, 1, 2, something like this. We'll do something like that. So let's do the limit as x approaches -1 from the left of f of x, and the limit as x approaches -1 from the right of f of x. Well, what are these going to be equal to? Well, let's actually just look at -1 and then come in along the left-hand side. So coming in from -infinity. Okay, so I'm coming in from -infinity along the left, and as I get close to -1, if I'm coming in from the left, I'm going to get closer, my f of x is going to get closer and closer to 1. Likewise, if I come in to -1 but from the right, so now we're coming in from the values from positive infinity, we're coming in, it looks like we're approaching -2, or at least this is definitely what I meant to draw. So as I come in from the right, I approach -2. And then one thing that we might also say is, well, what if I just wanted to know the limit as x approaches -1 without a superscript of from the left or from the right? So this object, well, notice the left-hand limit does not agree with the right-hand limit. So this does not exist. And the point to be made here is that limits exist if and only if the left and right-hand limits exist. So they have to exist first, so these cannot be undefined, and are equal. Okay, so if I wanted to compute a limit and I found that the left and right hand limits existed but they disagreed, well, then the limit itself does not actually exist. It's not a well-defined object. But the individual left and right hand limits are well-defined objects. Those are, I can sort of look at a graph and compute those if I want to. Similarly for continuity, so another definition. So now we can actually rigorously define what we mean by left and right continuous. So f of x is continuous from the left if the limit as x approaches c from the left of f of x is equal to f of c. And likewise, f of x is continuous from the right if, well, the same limit holds, but now we're going to do the right-hand limit. So the limit as x approaches c from the right of f of x is equal to f of c. And these are the rigorous definitions of continuity from the left and from the right. So going back to our example up here, in the example above, f of x is continuous from, well, which direction? Well, it's continuous everywhere sort of except at this -1 value. What is the, which side is the continuity actually on? Well, as I approach from the left, I actually attain the value that I am expecting. So in this example, f of x is continuous from the left at x equals -1, but it is not continuous from the right. I do not attain this value. I jump up to here, and that's where the function is actually defined. So, but not from the right. Okay, so given a graph, you can determine particular limits. You can say whether or not limits exist, and then you can also classify the continuity of a function from the left or from the right. Notice that maybe if I had like a filled in the dot right here, and then this was an open circle, then f of x would be continuous neither from the left or from the right, because its value would actually be not either of the two values that it is approaching. Okay, so the other topic that I had wanted to get to, but which I will not because this video is getting on a little too long, is limits at infinity. So that'll be another video, but for next week. So this is everything that will be covered in this first week, in which your quizzes and assignments deal with. Next week we'll finish up limits and then introduce the concept of a derivative. So have a good week, everybody. Good weekend, everybody, and I will see you all back, or I won't see you, but you'll see my lecture notes next week. All right.